Chapter 5 is about probability. Students often get a little nervous about probability. We're going to keep it as simple as possible. We're only going to cover sections 5.1 through 5.3. That's only half of probability. We're just covering the basics. So we'll go over just very basic probability rules, something called the addition rule and complements, and then finally the multiplication rule. And that's it, just half of Chapter 5. So if you're going through the extra practice or the practice quizzes or tests, just remember that we're only doing the first half of Chapter 5. Probability is technically its own course. It's a separate field, separate from statistics. We do just a touch of it to give us a sense of how probability works, and then that's it. So this is very brief, and I don't want you to overstress about probability. So what is probability? Probability is a measure of the likelihood or chance something occurs. Any kind of something, what is the probability or chance or likelihood that it occurs? We're studying basic probability so that we can better understand how to measure the reliability of the results measured from the data, everything we studied in Unit 2, which is Chapter 2, Chapter 3, and Chapter 4. We want to be able to measure how reliable those kind of results are based on the probability or likelihood of those results occurring. So all the decisions we make in a statistics class about is it reasonable, is it unreasonable, all stems from probability. So let's just think about flipping a coin. So standard American coins have a heads side. I don't know if you can see that. We call this heads because it's usually someone's face. And then we have what's called tails, which is the back side of the coin, which they change up a lot, but that's what we call tails. So any coin has what we call the heads side and then the tails side. And when you flip a coin, we have a 50-50 chance or a 1/2 chance of getting heads or tails. So the probability of each outcome when we flip a coin, so we can have heads, and there's a 1 out of 2 or 50% chance of that happening, or we can get tails, and that's a 1 out of 2 or 50% chance of happening. It's 50-50, 1/2 chance of heads, 1/2 chance of tails. So if we flip a coin 100 times and we compute the proportion of times the coin lands on heads, and we plot the proportion after each flip. So every time we flip, we're going to recalculate the proportion of heads. And the book has done this for us. And this graph is a little confusing at first. Let me see if I can make it a little easier for you to see. The bottom is the number of flips from 0 to 100. This is the probability of getting heads, or the proportion of heads. So the first couple flips, let's say the first flip, you got heads. So after that, just that first flip, you have a 100% heads, because it just landed on heads. Then you flip again, and it lands on heads again. So now again, you still have a 100% chance of heads, because both times you flipped, you got heads. Let's say the third flip, you got tails. Well, if I had heads the first time, heads the second time, and then tails the third time, the proportion of heads would be 2 out of 3. So that brings your proportion of heads down to about 0.67. And just kind of follow along. You don't need to write this down. Just kind of follow along. Well, let's say on the fourth flip, you got tails again. So now we have heads from the first two flips. And then we got tails from the third flip, and now we got tails again. So now our proportion of heads is 2 out of 4, which is 0.5. So now our dot's right at 0.5. Well, let's say on the fifth flip we get tails again. So we had tails, and let's say we got tails again. Now the proportion of heads is 2 out of 5. So it's constantly changing, which is 0.4, so our dot gets lower. It's constantly changing. Every time we flip again, the proportion keeps changing and changing and changing. So you'll notice the dots are just all over the place, changing and changing and changing. And now, maybe we got some heads in a row, so our proportion of heads is going up. It's constantly changing and changing and changing. Staying pretty steady at 0.6. We have a few more heads than tails. This is after 50 flips. We're just above or just below 0.6. We keep flipping and flipping and flipping. Now we're getting more tails and tails. We just keep flipping and flipping. And you'll notice that after 100 flips, we end up right at 50%. So hopefully that simulation kind of made sense. We're just flipping the coin and flipping the coin, and the proportion of heads keeps changing. But after about 100 flips, we kind of level out right at 0.5. And if we continued this and got up to, let's say, 1,000 flips, the whole graph would be pretty concentrated right around 50%. So the more and more times we flip, we're getting closer and closer to that proportion of 50-50. So hopefully that makes sense. That graphic is a little weird. It's from the book. So we have what's called the law of large numbers. Suppose we flip the coin 1,000,000 times with a simulator, which computers can simulate coin flipping. So let's say we flipped it 1,000,000 times with this computer program. Would our proportion of heads be close or far from 1/2? And hopefully you kind of see that it would be very close to 1/2, if not exactly 1/2. So this tells us that the law of large numbers, which the title kind of gives it away, the law of large numbers, states that the more times you perform a simulation, such as rolling a die or flipping a coin, the closer the sample proportion, so whatever ends up in your experiment, gets to the true proportion. So the sample proportion that you're getting from all your simulation is getting closer and closer to what we call the true proportion of the event, whatever that might be. So the phrase, the house always wins, you might have heard that for casinos. If you go to the casinos in Louisiana or in Las Vegas, they always say the house always wins, because the more people that play those games, the more and more and more they play, the more the true proportion will prevail. And the true proportion is that the house will win. So even though someone might win $1 million or $10 million or a new car every now and then, so many people play that the casinos will always come out ahead. I will say I've been to Las Vegas and I have gambled, and it's very hard for me to do, since I teach statistics, to sit there and just give away my money. So the next time you go gambling, just keep this course in mind and remember that the casinos are always going to win. Alright, so there's some vocabulary in this chapter that's similar to what we've heard before, but has a slightly different meaning in this particular chapter. So in this chapter, an experiment refers to any process with uncertain results that can be repeated. It's a little bit different than the experiments in chapter 2. It's a little bit more specific. Then we have something called the sample space, which they use a capital letter S for the sample space. It is a collection of all the possible outcomes for the event. So all possible outcomes. Heads or tails, the different sides of a die, whatever you're talking about, decks of cards, all the possible outcomes for the event is the sample space. An event, a particular event, which they use capital letter E, is a collection of outcomes from a particular experiment. So if we get heads, heads, tails from tossing a coin 3 times, heads, heads, tails, that particular outcome is called an event. So hopefully I'll clarify this in the next example. So the example they have in the book on page 234 is rolling a die. So I have a big die here. Hopefully you can see that okay. Let me get the other color. That might be easier. There we go. So a standard 6-sided die has the numbers 1 through 6 represented with dots on 6 different sides. Hopefully you can see them all. 1 through 6. And when you roll the die, it lands on one of those sides, whatever it might be. So if we roll a fair die 1 time, that means fair means it's not weighted, it doesn't have the same number on 2 sides, it's just a standard die that's fair. The different outcomes are 1, 2, 3, 4, 5, or 6. And that's represented with the number of dots that appear on that side of the cube. So there's 3, 2, 4, 1, 5, 6. So it's the number of dots on the side. There's a lot of variations, but this is a standard die that we use. So the different outcomes make up your sample space. And for a sample space, they usually use these curly brackets, and they list the outcomes with commas in between. So our sample space are the numbers 1 through 6. Then we have this particular event, roll an even number. So an even number on this die would be 2, 4, or 6 in this particular event. So if the event is roll an even number, and our sample space are the digits 1 through 6, what is the probability of this particular event? There's 1, 2, 3 possible outcomes in the event, and there's 1, 2, 3, 4, 5, 6 different outcomes, and we can reduce that to 1/2, and we can write that as a decimal 0.5, and we could write that as a percentage 50%. So you can write your answer as a reduced fraction, as a decimal, or as a percentage. They all represent the same number. If you're going to use the percentage, make sure to use the percent symbol behind it. All right. So there's two basic rules to probability. The first rule is that the probability of any event must be greater than 0, greater than or equal to 0, and less than or equal to 1. So the probability of any event has to be between 0 and 1. There could be a probability of an outcome that has 0 chance of happening, so that would be a probability of 0. There could be an event where the probability of occurring is 1, and that's 100%. So all probabilities must be between 0 and 1. 0 being 0% chance of happening, 1 being 100% chance of happening. A negative probability doesn't make any sense. The next rule, so that's the first big rule. All of our probabilities will be between 0 and 1. And the second big rule is that each individual probability, if we add them all up, the sum of the probabilities of all possible outcomes of an event must be exactly 1. So the probability of each event, each outcome, if you calculate all their probabilities, that has to add to exactly 1. So for the dice example, the probability of rolling a 1 is 1 out of 6. The probability of rolling a 2 is another 1 out of 6. Rolling a 3, 1 out of 6. Rolling a 4, where's the 4? Where's the 4? There it is. 4, 1 out of 6. 5, 1 out of 6. And finally, 6 is 1 out of 6. So there should be 1, 2, 3, 4, 5, 6 outcomes. If I add all of these up, if you remember adding fractions, the bottom stays 6. 1 plus 1 plus 1 plus 1 6 times is 6 out of 6, which is 1. So any event, the probabilities should all add up to 1. They might not all be the same. For a dice, they're all the same, but they might not be all the same number. But when we add them all up, they should equal exactly 1. So those are the two big rules of probability. They all have to be between 0 and 1, and adding them all up should equal exactly 1. Alright, so let's look at some probability models. This is just a list of all the possible outcomes and their corresponding probabilities. So again, these numbers can never be negative, and they must add to 1. So in this chart, I think this is different M&M colors. And so the probability of getting a brown M&M is 0, yellow is 0, red is 0, 0, orange is 1, and green is 0. So the only outcome here would just be orange. But none of them are negative, and they add to 1, so this is a valid probability model. This is valid. Over here we have brown has a probability of 0.3, yellow has a probability of negative 0.3. That is not okay. Not okay. The rest of them are fine. I think they do add to 1 because these two cancel themselves out. So this is not a valid probability model because of this negative value. Then we have this one, brown, yellow, red, blue, orange, green. If we add all these up, let's see, 1, 7, 9. I think it adds to the sum is greater than 1. So it is not valid. So all the numbers you see are fine, but when you add them all up, that's 3, 4, 7, 8, 9, it adds to over 1. And then this last probability model, all the numbers look good. If we add them up, they do sum to 1. And you can just, that's the shorthand for it, the sum equals 1. And then none of them are negative, none of them are greater than 1. So this is a valid probability model. So just some examples of what they would look like if they were okay or if they were not okay. Make sure none of them are negative, make sure none of them are greater than 1, and then make sure they all add to 1, which would be 100%. Alright, so there's some different types of events and they have some special names. We call an event impossible if the probability of the event is 0. For example, on a standard die, it is impossible to roll a 7. That just doesn't make sense. We can't roll a 7 because the numbers are 1 through 6. I also cannot roll a 0. That's not an option. I can't roll a 10. It just doesn't make sense with a single die. So an event is considered impossible when the probability is equal to 0. An event is considered certain if the probability of the event is equal to exactly 1. So this is going to sound a little silly, but the probability of rolling a number between 1 and 6 on a standard die is certain. You're definitely going to roll a number between 1 and 6 when you roll a standard die. So sometimes the probability of the event equals 1, and we call that event certain. It's definitely going to happen. Another example, if you flip a coin, you're definitely going to get heads or tails. That's certain. You're certainly going to get either heads or tails when you flip a coin. Alright, and then an event is called unlikely, also unusual. We'll use both of those words, unlikely or unusual, if it has what we call a low probability. And we generally say if it's less than a 5% chance, if there's less than a 5% chance of it happening, it's unusual or unlikely. So you'll see those words. We'll be using this concept a little bit later in the course, on in chapter 7, 8, and 10. You'll see that again, that anything with a low probability of less than 5% is considered unusual or unlikely. Alright, so we're going to learn two different ways to calculate probabilities. One is called the empirical method, and one is the classical method. Both are valid in different situations. Sometimes you can only use the empirical method, sometimes you can only use the classical method. Sometimes it's up to you which one to use, but we're going to learn about both. So the empirical method or approach, now this is not the empirical rule that we learned back in chapter 3, so they just use that same phrase, but it's not the same idea as chapter 3. So the empirical method is on page 236, and the probability of the event is what they call the relative frequency of the event. The frequency of the event, or how many times it occurs, out of the number of trials. We do this based on data given to us, or based on an experiment. Based on data or based on an experiment. So we actually run an experiment and then calculate how many times something occurred out of how many trials we did. So let me give you an example of that. So let's say a casino manager wants to approximate the probability of rolling a sum of 7 using a pair of dice. So I brought 2 dice here. So when you roll 2 dice at the same time and you add the dots together, so that would be a sum of 8, that would be a sum of 3, that would be a sum of 6, there's a sum of 7, there's a sum of 5, so it just depends. There's a sum of 6, there's another sum of 7. So, and you roll 2 dice, you add the dots together, so that'd be 4. So he wants to know what is the probability of rolling a sum of 7 using a pair of dice. So he grabs a pair of dice and rolls them 100 times and finds that 15 of those times he got a sum of 7. So he concludes, using the empirical method, that there's a 15% chance of rolling a sum of 7 on a pair of dice. And he got that by doing 15 out of 100, and he knows that that meant 15%. So how accurate do we think this experiment is? Is rolling a dice 100 times enough to say that that's probably pretty accurate? And that's just up to you. I would say 100 times is fairly accurate. He could have rolled it 1,000 times or 100 times in multiple days, and he probably would get pretty close to about the same every single time. So I would say that that's fairly accurate. We're going to find out in just a minute how accurate that is. Alright, so here's another example where someone sampled 200 people and asked them how they got to work. So the options were to drive alone. So 153 out of 200 drive alone. 22 of them carpool. 10 of them use public transportation. 5 of them walk. 3 of them use other means to get to work. And 7 of them work from home. And this is from a sample of 200. So you tally it all up and you get this frequency distribution. And now we're going to use those numbers to come up with probabilities for each of the categories. So what I'd like you to do is to start with 153 divided by 200, and I got 0.765. So I did 153 out of 200 to get that. And just continue that way. 22 out of 200 is 0.11. And then you should get 0.05, and then 5 out of 200 is 0.025. Don't round these. 3 out of 200 is 0.015, and then 7 out of 200 is 0.035. Now if I add all these up, they should add to 1.0 exactly. So I used my sample divided by my sample size to get the relative frequencies or the probability of each one of those occurring. So using those numbers that we just figured out, we're going to answer a couple questions. So this is from the book, those same numbers. The first question is, what is the probability that someone carpools to work? So we look at carpool, we have 0.11. So you can put 0.11, or you can put 11%, or some people might say 11 out of 100. Whichever way you want to say it is fine. Then the next question, in a sample of 1,000 people, how many would you expect to use public transportation based on this data? So if we look at our chart, we found that 5% of our sample used public transportation. So if I take 5% and multiply it by the new sample size, that gives me a predicted value or an expected value for how many people might use public transportation in a sample of 1,000 people. And we get 50. So out of those 1,000, we would expect 50 people to use public transportation. And the city of Houston and other big cities that use a lot of public transportation do these projections all the time so that they can anticipate just different amounts of people, different times of day. They collect all kinds of data and then project onto larger samples so that they can be prepared for whatever they need. So it's just a quick example of how to use the empirical approach. You take a sample, you calculate the probabilities based off that sample, and then you can answer questions using those probabilities. Then we have the classical method, or the classical approach. And this is often used in different games, carnival games, casino games, just different games. But this will only work for events with equally likely outcomes. So that all the probabilities must be the same, such as a coin or a dice or maybe a deck of cards depending on the situation. So all the outcomes have to have the same probability of occurring. So this one is not based on an experiment. It is based on what we call counting techniques. So we look for the number of ways the event can occur, which the book uses the letter M for that, over the number of possible outcomes, which the book uses a letter N for that. Also in your booklet of formulas, you'll see the empirical probability and you'll see the classical probability. So they're using number of E over number of S. So you just have to remember it's how many ways it can occur over the total. Alright, so let's look at an example of this. We're going to use the same scenario. We're trying to get a sum of 7, so with 2 dice. For a pair of fair dice, how many different outcomes are possible? Just in general, how many different outcomes are possible? We have 6 options on this die and 6 options on this die. And let me kind of help you think about this. If this pink die lands on a 1, the yellow die could land on a 1. It could land on a 2. So this pink one's still a 1. It could land on a 2. The pink one could land on 1 and the yellow one could land on 3. Then it could land on 4. Again, the pink one's still at 1. So far we have 4 different options. And then there's another option and another option. So that's 6 so far. Then if the pink die lands on 2, we have again those same 6 options for the yellow die. So that's 6 more, so that's 12. Then the pink one could land on 3, and then we have 6 options for the yellow one. Hopefully this is making sense. So we have 6 and 6. 6 options on the pink and combined with 6 options on the yellow. So that gives us 36 possible combinations. And then we have to think about what is the probability of rolling a sum of 7, or how many ways to get the sum of 7. So I usually have students make a little chart of what the pink die could land on and then what the yellow die could land on. If the pink die lands on a 1 and we want a sum of 7, the yellow die would have to land on a 6. If the pink die lands on 2, the yellow die would have to land on 5. If the pink one lands on 3, the yellow one would have to land on 4. If the pink one lands on 4, the yellow one would have to land on 3. If the pink one lands on 5, the yellow one would have to land on 2. And then if the pink one lands on 6, the yellow one would have to land on 1. And I believe that's all the different possibilities for having a sum of 7. So 1 and 6 is 7, 2 and 5 is 7, 7, 7, 7. So there's 6 out of 36 different ways to get a sum of 7, which reduces to 1/6, which is about 0.16 repeating, which rounds off to 0.17, which is about 17%. And if you remember back on the other slide, the casino manager, he got about 15%. So he got pretty close to the true probability of 17%. He got pretty close by rolling that die 100 times. There's also one that students always like to talk about, the probability of rolling what they call snake eyes. If you've seen casino movies or if you play craps at the casino, there's a roll called snake eyes. That's when you get a 1 on both die. It's called snake eyes. There's only one way that can occur. So there's only 1 out of 36 ways that can occur. And if you divide that, that's 0.0278, which rounds off to about 0.03, which is about 3%. Which, remember, we said if anything less than 5% is considered unusual or unlikely. So if you play the game craps, snake eyes has a really big payoff because it's so unlikely to occur.